Hello and welcome friends. In this video we will discuss about countable and uncountable sets theorem. The set is said to be countable if it is empty, it is finite or countably infinite. Friends, for detail about the definition of countable set and uncountable set, examples on countable set, you can watch our previous video on countable and uncountable set. Here I will write here in short what is meant by countable set. A set A is said to be countable. Set A is said to be countable if A is first condition is empty, second condition it is finite, and third condition countably infinite. That is, we have a function from the set An into the set A, and this function is a bijection, then the set A is said to be countable set. Now we prove theorem on this countable set theorem. Suppose if function f is from set A into the set B is 1 to 1 and B is countable, then A is countable. This is our theorem. Here in the definition of countable set you can see that there is a bijection. Bijection means the function should be 1 1 and onto, but in this theorem we have seen that there is only one condition, that is a 1 to 1. When this function is a 1 to 1 and if the set codomain set is a countable, then the set or domain set is also countable. Now if proof, if A is finite, this is first possibility. Suppose A is finite, then finite sets are always countable, and therefore the theorem is trivial in this case. The theorem is trivial in the case when A is a finite. Now if A is infinite, then suppose A is equal to, here A is infinite, let us see the Venn diagram. Here is my A, here is a B, and this is a function f. Then you can see that this is suppose f of A. So here f of A is the range set, this is the range set of A, and it is a subset of B. Okay. When A is infinite, the range set f of A is also infinite, but f of A is a subset of B. So this shows that B is infinite, since it has a subset, infinite subset. B is infinite but B is countable, so this set B is countably infinite. B is countably infinite. If B is countably infinite, by the definition of countably infinite set, there is a 1 to 1 correspondence between the set n to the set A. So we have a function phi from the set n to the set B, and it is defined as phi of n equal to Bn, where n belongs to capital N. That is, we have the elements of B are B1, B2, B3 dash dash dash. Okay. So you can see that these are the elements of B, but f of A is a subset of B, and hence the elements of B are also some elements of B are also elements of f of A. Suppose n1 is the largest number such that n1 is the largest number, not largest, it is a set of first number. First, if we see the members of f of A, there are some members in the set f of A, but from that number we can find the first number such that this element, let us call that element as a Bn1, belongs to f of A. Now then we have a n2 as a second number which is greater than n1 and is such that B and 2 belongs to f of A. Similarly, n3 is the third number which is greater than n2 and then B and 3 belongs to f of A. Then we get that this f of A equal to like this Bn1, Bn2 dash dash dash. Okay. So what we are doing, we have f of A is a infinite set, f of A is a range set of A, and range set of A is a subset of B. Therefore B has a infinite set as a subset, hence B is also infinite, but B is a countable by hypothesis. Therefore B is a countably infinite. B is countably infinite, that means there is a bijection from set N to the set B. We have taken that bijection is a phi, and for such that phi of N equal to B1. Okay. Then f of A is a subset, therefore there are elements of B are also members of f of A. We have chosen n1 is the first member such that Bn1 belongs to f of A. Then n2 is greater than n1 is a second member such that Bn2 belongs to f of A. Similarly, we arrive at the condition f of A equal to this set. Now let us see if my G is from f of A to n such that this G of Bnk equal to k for this k equal to 1 to n. We have taken this. Okay. So let us see, we need some space, so let us make some space free. I hope you get this idea how it becomes countably infinite. Now you can see that here if we draw the Venn diagram, this is my A, this is my B, this is f of A, then here is the Bn1, Bn2 dash 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 like. Now we are going to define the function g. This is function f. We are going to define the function g to n such that if this is 1, here is a 1, for this Bn2 here is a 2, for this Bnk here is a k, like this. Okay. Then this g is a 1 function and onto function. Okay. If g is a 1 and onto, we can define g o f from the set A into the set n. Then this function is a bijective function, that is there is this function is a 1-to-1, that is there is a 1-to-1 correspondence between the set A into the set n, and hence A is countable. So this shows that A is a countable set. One more theorem regarding the countable set. Here is the statement of that theorem. Theorem: a countable union of countable sets is countable. This is very important theorem in the countable sets concept. The countable union of countable set is countable. So let us prove this. Suppose let AI equal to we write this as a A1I comma A2I A3I dash dash dash. These are the countable sets for I is equal to 1 2 dash dash dash. Then we can see that each AI is countable. Now if we write explicitly the elements, then union of AI equal to if we write explicitly its elements of the A1, elements of the set A1, suppose here A1 equal to what are the element A11 A21 A31 A41 A51 dash dash dash. Now elements of A2 are A12 A22 A23 A32 A42 A52 dash dash dash. Elements of the set A3 equal to A13 A23 A33 A43 A53 like this. Okay. Now union of AI is equal to all these sets, union of all. So this is a dash dash dash, union of all these sets. Now we arrange the elements in a such a way that A11 is our first element, this is our first element. Then let us take A12 as a second, A21 as a third, A31 as a fourth element, then A22, then A13, then A13 here A14, then A14, then A24, A23, A32, A41 like this. Okay. Now how we have arranged? Suppose that these are the suffixes, I and J are the suffixes. This is an element I and J. Then we have added this I and J. I plus J is equal to K. Here K is equal to we get 2 3 dash dash dash, and I and J are the suffixes of the elements. So we can see that this A11 is my first element, then A12 is my second element, then A21 is my third element here, idea like this. Then next one A31 is my fourth element, A22 is my fifth element, then A13 is my sixth element like this. So we can see that this is the union set, union of AI. These are the elements of union of AI, and if we arrange these elements of the union like this by addition is same. Here A12 and A21 suffix s is equal to 3. So we have substituted this element are near 1 by 1. Then A31 is 4, A22 it is 2 plus 2 is 4, A13 is 4. So here we have arranged these three elements like this order. Then we can arrange this every element, and then there is a one-to-one equivalence between these elements and the set of natural numbers, and therefore union of countable set is countable. Now we prove that the Cartesian product of countable set is also countable. The Cartesian product of countable set is also countable. Theorem: the Cartesian product of countable set is countable. This is, let us take the two set Cartesian product A cross B. So here A and B, let us take A and B be countable sets. These are the countable sets, and A cross B equal to, we know that what is A cross B. A cross B is an order tuple where A belongs to capital A and B belongs to capital B. This is A cross B. Now if one of the two sets is empty, then we can easily here find that A cross B is empty, and empty set is countable. Now next possibility, one of them is finite. Suppose A is finite. Suppose A is finite. One of them is finite. We have considered the second possibility, that one set is finite. And suppose that the elements of the sets are here A1, A2 dash dash up to m elements, finite element, and obviously B is a infinite. So we write the element of B as B1, B2 dash 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 for our convenience. Okay. Now then what is A cross B? A cross B equal to, we can see that this is the collection, first A1 B1, then A1 B2, then A1 B3, then A1 B4 dash dash dash. Okay. Then A2 B1, A2 B2, A2 B3, A2 B4 dash dash dash. Similarly, if we continue and we get the final row as AM B1, AM B2, AM B3 dash. Okay. So like this we get the A set A cross B. Now we arrange these elements of the A cross B such that A1 B1, then A1 B1, then A2 B1 dash dash dash, AM B1 semicolon, A1 B2 comma, A2 B2 dash dash dash, AM B2 semicolon, A1 B3 dash dash dash, AM B3, like this, so on. And we can count every element and we can put it is in one-to-one correspondence. So these are the first m elements, 1, 2 up to m. this is my next m elements, this is m plus 1, m plus 2 up to m plus m. Like this, there is a one-to-one correspondence between this set A cross B to the set of natural numbers, and hence A cross B is a countable. A cross B is countable when A is finite. Okay. Now what happen if A is infinite? Then you can see that in this case also this set is countable. So let us take A is an infinite set. Suppose A equal to having elements A1, A2 dash 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 and B equal to B1, B2 dash dash dash. Let us take A cross B. A cross B equal to, we arrange this A cross B as first element A1, B1, second elements A1, B2, comma A2, B1, third element A1, B3, comma A2, B2, comma A3, comma B1, like this. Okay, and we define the function A1 comma B1 equal to, is image is 1, A1 comma B2, f of A1 comma B2 equal to 2, f of A2 comma B1 equal to 3, f of A1 comma B3 equal to 4, like this and so on. So you can see that if you arrange the A cross B in such a way that A1 B1 and A1 B2, B2 A1, like this, then there is a one-to-one correspondence between the set. This function f is bijective from the between the set A cross B to the set n of natural number, and hence the Cartesian product of two countable set is also countable. Now here we show that the rational number set, the set of all rational number, is a countable set. The set of all rational number is countable. The set of all rational number is countable. Set of all rational number is countable. Here, if the set of rational number ai, if we write this as a denominator 0 comma ai minus 1 comma ai plus 1 comma I minus 2 comma I, then 2 comma I dash dash dash. That is, if A1, then this set is 0 minus 1, 1 minus 2, 2, like this. A2 equal to 0 by 2, comma minus 1 by 2, comma 1 by 2, comma minus 2 by 2, comma 2 by 2 dash dash dash, like this. Then we can see that here is a one-to-one correspondence. This set AI is a countable. AI is countable. AI is countable for every I, and if we take the union of this AI, and this union of AI is countable, I is equal to 1 to infinity. This is nothing but a Q, that is the set of rational number, and set of rational number, we have proved one theorem, countable union of countable set is countable. So this union of AI is a countable. The AI is a countable. So this is a countable union of countable set, and hence the set of rational number is a countable set. Okay. Now we show that the set of real number is not countable. The set of real number is not countable. This is again very important to us. The set of real number, the set of real numbers is not countable. Now to prove this problem, this is my problem. Suppose the set of real number is not countable. We assume the contradiction. Assume that contradiction. We prove this theorem by contradiction. Assume that the set R is countable, and we write this set as R is equal to, suppose my elements are x1, x2 dash dash, xn dash dash. This is an countable set. Then we can construct an open interval in such that in is equal to here xn minus 1 divided by 2 raised to n plus 1 comma xn plus 1 divided by 2 raised to n plus 1. This is an open interval. Since why we have taken open interval? Since R is R is a real number, R is a set of real number, this is a set of real number, and this set is an open set. Therefore, for every element x of R there exists an open interval. So we have taken the open interval neighborhood of the point xn, and see the length of this open interval. In is of length 1 divided by 2 raised to n. Here n equal to 1, 2, 3 like this. Then we can see that here I1 equal to I1, which is neighborhood of the point x1. This is an open interval x1 minus 1 divided by 2 square, x1 plus 1 divided by 2 square. This is an open interval, and length of each in is equal to 1 divided by 2 raised to n. So I1 is of length 1 by 2, I2 is of the length 1 divided by 2 square, I3 is of the length 1 divided by 2 cube, like this. Now here we have taken R is countable, so R can be written as a union of countable set xi. I is equal to 1 to infinity, but xi is a subset of union of in. I is equal to 1 to infinity. And what is union of in? Union of in is 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus plus plus, and this is maximum equal to 1. We can see that this is a geometric series whose length is equal to 1. So we are saying that this R is a set of real line is contained in the interval whose length is 1, and this is very absurd thing. This is not possible. Whole real line cannot contain in an interval whose length is 1, and hence this is not possible. Therefore this set, this R is not a countable. This is contradiction due to the assumption that we have assumed that this R is a countable set. Okay, so friends, I hope you get the theorems regarding the set of countable and uncountable set. We have proved that this Cartesian product of countable set is countable, countable union is countable, and the set of rational number is also countable, but the set of real number is not countable. Okay, thank you for watching, and please give me your suggestions. I welcome your suggestion to improve the quality of video, and so that you will get more and more videos which encourages me, and also you will get very effective videos on the these concepts of mathematics. Thank you for watching.